Right, it's recording now. So I've just displayed the first page again for the sake of the recording. So I've defined a transposition, which is a 2-cycle, given an example of a 2-cycle in S6. And now I'm going to show that every n cycle for any n bigger than or equal to 2 can be written as a product of transpositions. So I'm interested in writing permutations as products of transpositions. So I'm starting off by writing cycles as products of transpositions. Okay, so let's just do an example of this. Well, let's look up, say 1, 2, 3, 4, 5. That's a 5-cycle. It's easy to check that this is the same as 1, 5, 1, 4, 1, 3, 1, 2. So these two permutations are equal. The one on the left is a 5-cycle, so it's just got one orbit with more than one element. And the thing on the right is a product of transpositions. Notice these transpositions are not disjoint. In fact, they all have a 1 in common. But nevertheless, this is a product of transpositions. So what it says is that this 5-cycle can be achieved by just swapping 2 numbers at a time. And you need to do that, in fact, 4 times. So you first swap 1 and 2, then you swap 1 and 3, swap 1 and 4, and finally swap 1 and 5. And you'll have done the same thing as what this 5-cycle does. So let's just perhaps just check that. Look at this permutation on the right. Where does this send 1? Well, it sends the transposition right at the right-hand side sends 1 to 2, and these other 3 transpositions fix 2, so 1 ends up getting sent to 2. Where does 2 go according to the one on the right? Well, 2 gets sent to 1, which then gets sent to 3. These 2 fix 3, so 2 gets sent to 3. And so on. You can check that indeed these are equal, because they send each of the numbers 1 to 5 to the same place, and all the numbers, if there are any other numbers, are fixed by both. Okay? But just as a remark, so this is an example of the remark at the top, but this thing is also equal to, for instance, to 1, 2, 2, 3, 3, 4, 4, 5. You can check that. So that's another way of writing this as a product of transpositions. Okay, I'll let you check that that's also equal to that. And here's another way of writing it. Let's just slip in 4, 5, 4, 5 there. So all I've done here is taken this decomposition as a product of transpositions, and I've slipped in a 4, 5, 4, 5, which doesn't change it because 4, 5, 4, 5 is just the identity. Because it swaps 4 and 5 and then it swaps 4 and 5 back. So I'm doing that to make the point that this decomposition into a product of transpositions is not unique. Both of these had 4 transpositions, but that number 4 is not significant because here's one with 6. 1, 2, 3, 4, 5, 6. Okay? So every cycle can be written as a product of transpositions, but not in a unique way. Okay? But the point is that every cycle can be written as a product of transpositions. So hence, every cycle can be written as a product of transpositions. But we also know that every permutation can be written as a product of cycles. That was in just what we did just before the break. So given that every permutation can be written as a product of cycles, and that every cycle can be written as a product of transpositions, putting those two things together gives us that every permutation can be written as a product of transpositions. So, since every permutation We're now talking about permutations of finite sets. When I use the word permutation rather than bijection, we tend to be talking about finite sets. So since every permutation can be written as a product of cycles, in fact disjoint cycles, we conclude, and this is the important thing, that every permutation can be written as a product of transpositions. Okay, so every permutation can be written as a product of transpositions, but not in a unique way in general. Okay, so this is an important fact, that we can build up any permutation just as a product of transpositions. Very simple permutations that just swap two numbers at once and fix everything else. So let's just have another example, which I've already referred to. If we take the identity permutation, how do we write that as a product of transpositions? Well, for instance, we can just do it as 1, 2 times 1, 2. I'm not stating which set I'm acting on here, but it's got to be at cardinality at least 2. But the identity element can be written as 1, 2 times 1, 2. So that's a product of transpositions. So the identity element can be written as a product of transpositions. Now, as we've said, the decomposition into transpositions is not unique. In general, there's lots of ways of doing it. But what is unique is the parity of the number of transpositions. In other words, it's either always even or always odd. So, for instance, the identity element can be written as the product of 2 transpositions. It can also be written, suppose we were working in S4, for instance, it can also be written as the product of 4 transpositions, or 6 or 8, but it can never be written as the product of 5 transpositions. So we say that the identity element is even. It can never be written as the product of an odd number of transpositions. Another example, suppose I took 1, 2, 3. Well, that can be written as 1, 3 times 1, 2. And it could also be written as 1, 3, 3, 4, 3, 4, 1, 2, if we were working in S4. So I can write 1, 2, 3, this 3 cycle, as the product of 2 transpositions, or of 4 transpositions, or of 188 transpositions. I can never write it as the product of 17 transpositions. So once I know I can write a permutation as a product of an even number of transpositions, you can never write it as a product of an odd number of transpositions. And that's a theorem, and that means that permutations are classified into even permutations and odd permutations according as to whether they can be written as a product of an even number of transpositions or an odd number of transpositions. So this is a very important theorem. So let me state it. So we're talking about finite sets here. So the background is we know that any permutation can be written as a product of transpositions, but no permutation in Sn can be expressed both as a product of an even number of transpositions and as a product of an odd number of transpositions. No such permutation exists. So it's either odd or even, but not both. Well, I'll just indicate how you might prove this. In fact, Fraley gives two proofs. And there are lots of ways of proving this, depending on your personal preferences and depending on what bits of maths you want to use. So Fraley has two proofs, one of which is to do with counting orbits, which is quite a nice proof. But the other one that he uses is a kind of linear algebra proof, which I'll just outline here. You can look at the details in Fraley. The way the proof goes, and so this is not a properly written out proof here, you can look at the proof in Fraley, but the idea is we think of permutations not as acting on the numbers 1 up to n as numbers, but on the rows of the n by n identity matrix. So suppose, well, this is the 4 by 4 identity matrix. So there's the identity matrix. That's actually for n equals 4, but I could do this for any value of n. And suppose I think of the rows as the things on which my permutations are acting. So this is an n by n, in this case n equals 4, so there are 4 rows. So I'm going to permute the rows. Okay? So any permutation will permute the rows, and then I'll get some new matrix. So by applying a permutation sigma to the identity matrix in this way, I'll get some new matrix. I mean, it might be the old one, depending what sigma is. If sigma is the identity, I'd get the old one back. But in general, I get a new matrix. Now, suppose I write sigma as a product of transpositions, I will get the new matrix just by swapping 2 rows at a time. So each transposition just swaps 2 rows of this matrix. And then I'll get sigma by swapping 2 rows, then another 2 rows, and another 2 rows. And every time I swap 2 rows of a matrix, what happens to its determinant? If I swap 2 rows of a matrix, a square matrix, what happens to its determinant? This should be a fact from your linear algebra. If you swap 2 rows of a matrix, its determinant gets multiplied by -1. Does that sound familiar? You should have seen that before. Okay? If you swap 2 rows of a matrix, any square matrix, the determinant gets multiplied by -1. So every time you do one of these transpositions, you get a -1 coming into the determinant. Now in the end, you've got some matrix, and its determinant is either +1 or -1. It can't be both. Now if you did an even number of transpositions, the determinant would flip -1, 1, -1, -1, +1, etc. But you'll end up with +1. If you did an odd number of transpositions, you'd end up with -1. You can't have both an even number of transpositions and an odd number of transpositions, both equaling the same permutation. Otherwise, you'd have a matrix whose determinant was both +1 and -1, which can't happen. So that's the idea behind the proof. So I urge you to have a quick look at the proof written out properly in Fraley, but it hinges on the fact that if I swap two rows in a matrix, then the determinant changes by a factor of -1. Okay, so I'll leave you to look at the proof in Fraley. This is a very important result, okay? So that's the linear algebra proof. You may prefer the other proof, which is about counting the size of orbits. So this leads us to the definition of even and odd permutations. So suppose I've got an element of S sub n. So n here is some positive integer. So the permutation sigma is set to be even if and only if sigma can be expressed as a product of an even number of transpositions. And this definition makes sense because we know that sigma can be written as a product of an even number of transpositions or as an odd number of transpositions. If it can be written as a product of an even number of transpositions, we call it even, and otherwise we call it odd. And it's really the otherwise bit that makes sense. We can't have a sigma being both odd and even. So odd means it can be written as a product of an odd number of transpositions. We probably just ought to say something about the case n equals 1. If n equals 1, there's only one permutation, which is the identity, and I couldn't do the 1, 2, 1, 2 trick because I wouldn't have a 2 to play with. So we just define that to be even as a separate case. But since we're not very interested in n equals 1 usually, that doesn't often arise. So I couldn't do the 1, 2, 1, 2 trick with n equals 1. Okay, so we're now dividing up or partitioning our permutations up into even and odd. So let's just have another example. Similar to the one we've already done. Just to reinforce the idea, suppose we consider this 4 cycle in S6. Well, I can write this, for instance, as 1, 6, 1, 5, 1, 4. I can write it in lots of other ways as a product of transpositions. Here I've written it as a product of 3. In fact, 3 will be the smallest number you could use. Any other decomposition as a product of transpositions will have an odd number of transpositions. So this is an odd permutation. So 3 transpositions. And 3 is odd. So 1, 4, 5, 6 is an odd permutation. It's just slightly unfortunate that this is a 4 cycle. 4 cycles are odd. Okay, so if you've got a k cycle, then that will be even if and only if k is odd. It's just slightly annoying, but that's the way it is. Okay? So in general, a k cycle is odd if and only if k is even. So don't forget that. So 4 cycles are odd and 3 cycles are even, for instance. Well, what we're going to do now is put all the even permutations in a bag and all the odd permutations in a bag. But it's the even ones that give us a subgroup. And we call this subgroup AN. Well, we haven't proved it is a subgroup yet, but it will be. It's called the alternating group, and it sits inside the symmetric group. Okay, so we're putting all the even permutations in a bag. My curly brackets are getting more and more degenerate. Sorry about that. Now, so what we've got is our symmetric group. And some of the permutations are even, and we've put those all together and called it AN, and the rest of them are odd. So that's the complement of AN. And one of the elements of AN is the identity, but in general there'll be lots of other elements in there, and then there'll be some odd ones. And the first remark to make is that these two cells, because this is a partition, because everything is either odd or even, so this is a partition, these two cells have got the same number of elements. So this partition divides the symmetric group up into two equal parts. So why is that? So this is the complement. These have got the same number of elements. Well, if they've got the same number of elements, then each one must have a cardinality of n factorial over 2, because the symmetric group as a whole has got cardinality n factorial, remember. So each of these sets has got half of that as their cardinality. And the proof of this claim is, well, how do you prove that two sets of have the same cardinality? You've got to define a bijection from one to the other. Okay? So I'm going to define a bijection from AN to the complement. I'll call it F. By the way, I'm using this notation to denote the difference between these two sets. You've probably seen it before. Some people use a minus sign rather than the backslash. This is the complement of AN in SN. So it's everything that's in SN but isn't in AN. In other words, it's everything that's odd. So I'm defining a bijection. Well, I'm defining a function at the moment which will turn out to be a bijection from AN to the complement. So for a permutation in AN, I'm going to define f of sigma to be what? Well, sigma is supposed to be even. How would I get an odd permutation from sigma? Well, I just multiply it by, say, 1, 2. So this is really composition of bijections. So sigma is even, so that can be written as a product of an even number of transpositions. The permutation on the right must be odd, because if sigma can be written as the product of an even number of transpositions, another factor of a transposition will change the even to odd, because I'm adding 1 to an even number, so that's going to be an odd number. So this indeed is in Sn minus An. Okay? So that definition does make sense. For every even permutation, the thing on the right is an odd permutation. So that is a function from the evens to the odds. So that's certainly a function that does what it says on the tin. It does have domain AN, and it does have codomain, the complement of AN. And the claim is that this is a bijection. Well, I'm not going to prove that now. I'll let you check that. We need to check that F is a bijection. That's quite straightforward. If you can't do that, then ask in the tutorial next week. It's just the easiest way is to show that f has an inverse.